let me, what's that?
I don't think the video from the last lecture is posted.
You might be right. I think I was, uh-oh. I was about to do it, and then I think I got distracted. Let me begin with a word of prayer. So, dear Heavenly Father, we thank you for this day, and again, I just thank you for this class and this time we have to study your creation. Just guide our thoughts today, Lord. In your name I pray, Lord Jesus. Amen. So yeah, we defined manifold last time, right? Which is a set together with an atlas, right? Any particular atlas can be extended to its so-called completion, to a maximal atlas, which has all possible compatible charts. And the thing I was a little bit unable to say last time, and I can only partly say because we haven't quite defined everything yet, but let me just get it out of my system, all right, is for a given set, you might have more than one atlas possible on the set, right? And those different atlases don't even have to be compatible, right? So the example I want to talk about today eventually is just the real line. The real line, we can on the one hand give the identity map. That gives a global chart, right? That's the one. But we could also give the cube map, and that also gives a global chart. However, the cube is not an admissible chart. It's not an admissible chart with respect to the usual identity chart, because the inverse function to the cube is the cube root, which is not differentiable at 0. So that means that the cube chart is incompatible with the identity chart. So, and yet there's a maximal atlas which contains the cube chart in it, and all other compatible charts and all other compatible maps on the rails that are compatible with the cube. So there's the atlas, the standard atlas, all compatible charts with the identity map on the rails, but there's also the maximal atlas, which is all charts which are compatible with the cube map on the rails. And these are not the same maximal atlas, all right? And yet, as Lee describes, both the cube chart and the identity chart, they both induce the same topology on the reals. So as a topological space, we're talking about the same just standard Euclidean topology on the real line. That standard Euclidean topology can be given two distinct differentiable structures, right? The standard one and the cube one. And the thing that was tripping me up is I was reading later in Lee's chapter where he explains that in fact the standard differentiable structure on the real line and the cube structure, the cube maximal atlas on the real line, they're what is called diffeomorphic, which means that you can find a smooth map from the one to the other with a smooth inverse. So while they are technically different maximal atlases, they are in some sense the same smooth structure in the sense that there exists a diffeomorphism from one to the other. And yet, that doesn't mean that the cube map is itself compatible with the identity map. So this is the circle of ideas that I was getting a little bit tripped up on last time, and I kept half saying it, and that's it. Now, we haven't defined diffeomorphic yet. We need to get there, all right? So, but I do want to work on the homework problems you guys are stuck on too. So let me see if I can just get to the main definitions I wanted to share with you guys today. We'll get those out of the way, and then we'll go and we'll try to work some of the examples, because I did that on purpose. Like, I know you guys don't know those examples yet. The purpose of the homework is for you to try to like understand them and work them out, because we don't have enough class time to do all the examples. All right, so, and again, as I was saying, you can go light on the topological aspect of the examples. Try to focus more on finding the inverse formulas and understanding how the transition functions are actually smooth. And you don't have to belabor it either. Like, I'm not looking for you to actually show me the derivative is such and so forth, and it's defined on the domain. Like, you can look at it and go, oh, okay, well, that's smooth. Like, that's, all right, so let's see here. There's a lemma in Jeffrey Lee's book, which is worth keeping in mind. It says, this is lemma 130 from page 13. I'm just going to read it because we'll use it on occasion, okay? Like, Let M be a set with an atlas, and if you've got U and UX and VY charts compatible with the atlas, such that their intersection is non-empty, then you can look at the charts that are formed by you can use the intersection of the chart domains and the restriction of the maps. So like, I'll just draw a picture. So like, if you've got this, and you've got this, all right? And this one's got X, and this one's got Y, then what he says is that if you look at U intersect V, and then the map X restricted to U intersect V, and if you look at U intersect V, and the map Y restricted to U intersect V, all right? Well, these are also charts which are compatible with the given charts U, X, and V, Y. So if we're talking about a maximal atlas, then these will also be, like charts which are available to you. And he also says that another thing he does, which is kind of sneaky. So like here, X, let's say, I chose poorly in my picture. Let me make this go to side a little bit here. Whee! All right, so over here is Rn, right? And so down here is my quote-unquote X of U, right? Subset of Rn. And what he says is that also, if you have an open subset of X of U, right? So if you have like some subset of the X of U, so maybe it's like, like this or something. Oh man, this is trash. You should have thrown this out. All right. If you have some open subset of that, then if you look at that, you can use that to build yet another chart, okay? You can build a chart which takes that as its X of U, quote unquote. In other words, let me try to, he says, well, let me use yet another letter. So maybe up here, we call that W, equals to X inverse of O. This is O, all right, an open set down there. Then if I was to use W and then X restricted to W, that would also be a chart in the maximal atlas. So these things, ways of creating new charts from old, are like important for certain arguments here and there. Yeah.
What's O?
Just O is an open subset of down here. So just some open set. O is a subset of X of U. This is an open. I'm sorry. It's yeah, fine. Let me make it all funny there. Is that better? I'm not saying it's homomorphic either. Okay, whatever. Enough about that. And then if you look at proposition 1.32, it's again this statement that the atlas for a manifold induces a topology which has a countable basis, and it's Hausdorff and so forth. So anyway, I don't want to belabor that. All right. Okay, so let's talk about smooth maps. So if we have, here's M, all right, here's N, and I have a function going from M to N like this, right? Then to say that F is smooth, to say that F is a smooth map, all right, from M to N, what that means, well, here's how Jeffrey Lee defines it. And it's kind of annoying because this is the one problem with looking at both books, is like inevitably he will take the definition to be one thing and prove the other, and then the other Lee will take the proved thing in Jeffrey's. John will take the thing Jeffrey proved to be his definition. So it's like they're equivalent statements, right? So that's one sort of annoying thing about looking at both books at once. But what it really means is, like, to study this, you really need to allow for both ideas to characterize the smoothness. And so because one or the other might be more convenient for doing a problem. But anyway, so the point here is that, let's see here if I can say it. If at P and M there exists a chart, so we take P and M, P there, right? There exists a chart, V comma Y from AN. So like over here, you've got F of P, all right? And so the point is we want V comma Y, an element of the atlas of atlas of N. And this is this definition is given with respect to maximal atlases. Okay, so like A sub N and A sub M are going to be maximal atlases. So that's there. And let me draw a picture. Draw a picture here. So here is your U. Over here is the V. All right. And let's see here. The UX is where? What's that? I mean, of course, here U comma X is in the atlas, the maximal atlas for M. Right. Now we have to be able to do this setup for each point in the manifold, okay? And what else do we need? We need that F of U, where F of U is a subset of V, all right? Let me read it more formally. If there exists a chart, V comma Y from A sub N with F of P and V, and a chart U comma X from A sub M with P and U, such that F of U is a subset of V, and such that Y composed with F composed with X inverse is class CR. So there exists all this such that, oops, this is going to be, well, I guess I should draw a picture, right? So down here, and over here. So here we're looking at X of U, right? Over here we're looking at Y of V. And okay, so let's see here. So X does like this, right? Y does like that. And of course down here we're talking about, this is Rn, and this over here, they don't have to be the same dimension, okay? Rm. And to say F is smooth, all right, at the point P means that there exists a chart U and a chart V such that the image of U under F is a subset of V, right? F of U is a subset of V. But here's the kicker is that the local coordinate representative of the function is smooth. What do we mean by local coordinate representative? I mean, what you put down here, basically, we steal the formula for F down to here. So follow the map. All right, guys, follow the map. So F goes in the middle. And the last thing that happens is Y. So we compose with Y last. Wait a minute, compose with Y last. I'll learn eventually. And to start with, we have to go the opposite direction of X, right? So X goes like this. So X inverse. And now to be fussy, the Y composed with F composed with X inverse is supposed to be judged as a mapping from X, this is a little bit complicated, the inverse image of V intersected with U. So the inverse image of V intersected with U mapping to Y of V. Like that's the context that we judge the smoothness here. Now the reason he gives this definition, all right, is so that if you do this with respect to the maximal atlas, then we can show that, well, I guess let me finish talking here. So if there exists all this, right, then that shows that F is smooth at the point P. Right? Now he has the definition for like R times CR. It's CR at the point P, meaning that this function is a CR differentiable function from, you know, Rn to Rm. So I'm just going to focus on the smooth case, okay? Like this would need to be a smooth map from Rn to Rm. Like I was talking about last time, that would mean if you calculate the Jacobian matrix of it, you know, it would be a matrix of smooth partial derivatives. All right. So this was done with respect to a maximal atlas, in part so that he can put the next exercise 1.53. Did I assign that to you guys?
Which one?
1.53? 1.53?
I didn't get that far.
I thought about it. I don't know if I did or not.
I'm not sure. Or else do like 140.
I don't mind doing it for you if I did anyway. But the question is, how do you, and maybe I didn't though, because the question of continuity really is a question of, you know, topology. But the exercise 1.53, which follows the definition, is to show that a CR map is continuous. All right, and so like, so if we have that the map is smooth at the point, then that means that there's this transition function, this local coordinate representative, which is smooth. So how would you show that F itself is continuous? Well, you basically just try to solve this for F, like write a formula for F. What is F equal to? If I want to write it in terms of this, right? How can I get equality here? What do I do? Uh-huh. Very good. And over here? Yeah, composed with X, right? So that's an identity which is true for certain points, right? It's true at the point P, pretty sure. And what could you say about this? What is this? See what this is the composition of? It's the composition of this map, and this map, and that map, right? One of the things you'll learn in topology is that the composite of continuous maps is continuous. But if we take this tact, if we take a maximal atlas, which is assumed, we're assuming in that context that all of the coordinate maps, all the coordinate charts are themselves homeomorphisms, right? That they're continuous bijections. So that means that we're looking at the composition of a continuous map. Well, this is a smooth map on Rn. A smooth map on Rn is automatically continuous, right? Just like Calc 1, we learned differentiable implies continuous, remember? So that's still true for multivariable. And so we were looking at the composite of continuous maps, therefore F is continuous, right? So now that said, proposition 1.55 on page 22 of Jeffrey Lee's book is kind of more where it's at, which is, he says, if we know that the function's continuous, we can check its differentiability just by using representative maps with respect to the, you know, just representative maps, not necessarily a maximal atlas. The using the maximal atlas allows you to get at the continuity. But yeah, Jeff?
How do we know that that map is smooth?
That's the definition of smooth map. Definition of a mapping from manifold M to a manifold N being smooth is that the local coordinate representative is smooth.
Okay, how do we know that it's
And I should say more specifically, every possible local coordinate representative is smooth at the point in question. So like there's a, you know, there are certain, basically any collection of charts which contain the point P and for which there also, there also has to, and then over here, all of the corresponding charts on N, which actually contain the image f of p, right? You have to look at all of those, all of the relevant charts. If there's other charts on N that don't even touch f of p, then we don't have to check those, logically speaking. Like, well, not only do we have to check them, they're not given to you. You don't get any information about those in the definition. The definition just concerns all possible, if there exists a chart that sets up, that matches the structure, then it has to be that the local corporate court representative is smooth.
You're just checking that they're differentiable?
Smooth.
How do you check that a chart is smooth?
It is infinitely differentiable.
Well, how can you know that?
What do you mean? Like, on Rn, are we talking about, like, what's the definition of smooth? Smooth means that you can take as many partial derivatives as you like.
How would you know that you can do that?
Well, it depends on the example. For the one we had before class, like the square root of 1 minus y squared, you can differentiate that, and you can keep differentiating it, because you can differentiate a square root function, and,
Okay, so it's not like a general method.
no, I mean, think generally speaking, as he says, as I think Jeff, is it Jeff really? See, I've been reading both books, which is probably a bad idea. I need to stop because my mind is starting to like fragment. And, but at some point, the other Lee fesses up that there are basically 3 ways to check that a mapping is smooth. All right, and the 3 ways are as follows. This is from page 37 of John Lee's book. He says, you write the map in smooth local coordinates and recognize the component functions as composition of smooth elementary functions. That's the one way. You exhibit the map as a composition of maps that are known to be smooth. That's the laziest way possible. And then, or you use some special purpose theorem that applies to the particular case under consideration. So, in short, the formula is something we already talked about. How to calculate derivatives of in calculus is really the answer to your question, Jeff, I think. Yeah.
So generally, to show that f is smooth, we want to take arbitrary charts in both ends and show the differentiation function.
We definitely don't want to do that, but that's the definition.
Is that the general approach? Taking arbitrary charts.
That's the definition, which is super convenient for definitional purposes. What we want to do is just to check the map with respect to a given atlas. We don't want to check a map with respect to a maximal atlas because there's infinitely many things to check. Right? So like the way to do this, and this is the proposition 1.55, let me write it out here. I mean, if I didn't do anything else, the answer to your question would be yes, right, exactly. But pragmatically speaking, we don't want to do that because that's like a lot of things to check, right? So instead, thankfully, there's this proposition, 1.55. Let's see here. Jeff Lee. I really wish they had different last names. I'm going to go crazy doing this pretty soon. So he says, let u alpha, comma x alpha. All right. Ew. That's gross. He's using A as the index set. I refuse. Alpha in index set for M. Ha, take that. And V beta, Y beta, such that beta is an element of the index set. I'm going to use a lambda for N. All right. Atlases, let blah and blah be atlases for M and N respective. Notice that I am not saying maximal atlas, just atlas, right? So it's not necessarily complete, all right? And then here's the thing. A continuous map, F, from n to m to n. All right. A continuous map f from m to n is smooth. Actually, he says he says CR, but I'm trying to keep it smooth, you know. So let me. I don't want to have to differentiate between. Yeah, thank you for that. Is is smooth if for each alpha in lambda m and beta in lambda n, the representative map y beta composed with f composed with x alpha inverse is smooth on its domain x alpha, which is f inverse of v beta intersect u alpha. I guess we can't get away from that, can we? So the assumption here, though, is that the mapping is continuous, and that is what frees us. Like that ultimately is, if you look at his proof, that's what gets him. He's able to take an arbitrary chart in the maximal atlas and show that he gets that condition just basically building off of this data. Let me show you the critical calculation in this whole business. See, the real point here. And by the way, one other thing I should say before I forget is that it could be that the intersection with that inverse image and U is empty. That could be the empty set, in which case there's nothing to check. So this is basically saying for all for all actual coordinate representatives, check the smoothness, and if it doesn't work. So anyway, let's see here. Let me read you a sentence that is important here. He says, without worrying about domains, the point is, now let's see, I need to tell you the context here. Suppose we have, all right, so here's basically the, heart of the matter. So the heart of the matter is that if you have, a local coordinate representative, F composed with F composed with X inverse, smooth. Representing F at P, all right? And so if you'll allow me to recreate the picture here, well, let me not. I guess I need to, the picture is necessary. All right, so here's the picture. Here's my U, my V, all right, my X, my Y. But there's more. Suppose you have another representative, right? Another representative that also gets P, all right? Let's call it U prime. And it picks up here on F of P, right? Call that V prime, all right? So there's Y prime and X prime as well. So let's suppose that, you have a representative, Y composed with F composed with X inverse, but you got another choice. You got an X prime chart and a Y prime chart, also in the same, target area. And you're given that the local coordinate representative with respect to y and x, or if you like, the u and the v chart domains, is smooth. Okay, well then, let's see here if I can. It might be helpful to just picture these as separate copies of Rn. You don't have to view each coordinate chart mapping to the same Rm. You can separate them. It's helpful sometimes for these kinds of diagrammatics to do that. All right. So okay, so we're given. What are we given? We're given that y composed with f composed with x inverse is smooth, right? Which is like this guy. Man, I chose poorly. My diagram, I chose poorly. See, because I should have switched the order of the primes and the other things, it would have made a prettier picture. But I'll deal with it. It is what it is. So this is the given. We know that that's smooth. All right? We're given that. What we'd like, right? What I want to argue is that, in fact, this one that goes from here to here, right? This one would be y prime composed with f composed with x prime inverse. I'd like to argue that that is necessarily smooth as a map from Rn to Rm on the basis of the given smoothness of the unprimed map. So let's see if you, I bet you can get it, Jeff. If you did it once today, I bet you can do it again. We're going to play the mapping game. So what's the formula here? What's the formula for y? I got y prime composed with f composed with x prime inverse, all right? And I want to get that related to y composed with f composed with x inverse. I'm given that this is smooth. This is given to be smooth. I'm trying to prove that this is smooth. What do I do?
Y inverse on the front,
So I need a y inverse,
and then a Y prime.
a y prime. Okay.
On the other side, X and X prime inverse.
Very good.
Let's go.
Now my question to you is, why is that smooth?
Because we know that the middle thing is smooth, so then
Let's see here. What is?
one of the many smooth.
Well, but why are those smooth? Why are those?
Inverse is the smooth maps, right?
No. Easier than that. So, what was the definition of? So we are assuming, of course, that these are compatible charts. That should be said. Assuming x prime and y prime are compatible, respectively, with x and y. That says that the transition functions are smooth by definition, right? So those are these guys, right? What's this map here? So x prime composed with x inverse, right? And over here, you could do like this one, I guess, if you wanted. That would be y prime composed with y inverse, right?
In this specific example, I think you'd want to go the other way. For the X's.
Oh, yeah, well, the good news is that part of the definition of compatibility is it goes both ways, right? So this is also, but granted, Jeff, let's see here. So this would be x composed with x prime inverse, right? Those are the transition functions of the compatible charts. Those are assumed to be smooth. Who put that there? All right, that's it. You're going down. Going down. That's it. I've had enough of your lip. Get down. I know there's a way this goes down. Haha, take that. Yep, that's right. Yeah, your day is done here, sir. Oh. Haha. There. Try to poke me now. Stupid furniture. All right. All right, guys. So that's the definition of a smooth map. The definition of smooth map Listen, don't get lost in the domain business. That'll make sense when you actually get into an example. The issue is the definition to remember is simply this. A mapping is smooth from one manifold to another if all of its local coordinate representatives are smooth. And that technically the logically primary definition is made with respect to a maximal atlas to avoid pathologies, but thankfully we have this proposition which says it suffices to check on just an atlas, which is wonderful. Because this is the primary thing which gets you the rest of them, right? Because if you've got smoothness with respect to a token representative and you have smoothness of the transition functions for the compatible charts, then you get smoothness for the other representative. All right. And so if you were like me, we were taking this class, you're like, can I see an example? And then any professor who knows what they're doing would be like, no, not in class, because the example would be so lengthy. Or it would be trivial and not really serve to illustrate the, the thing. Although, there are some decent examples in this book. All right. So let me continue here. So, all right. So that's the definition of smooth. What about a function rather than? What does this look like if instead of being n, you just have like a real valued or a possibly a complex valued function? What's the definition of a smooth map on a manifold look like then? Oh, by the way, if this is the case, we say that f is an element of like C infinity Mn. That's the set of all smooth maps from M to N. Now, if instead of having n here, you put the reals, so we talk about a real valued function on a manifold, all right? Excuse me. A real valued function on a manifold, then in that case, this definition sort of collapses a bit. So if you've got, here's your M, here's F, you're just going to the reals, right? Then if this is the point P, you've got your chart X down here, X of U. To say that F is smooth is to say its local coordinate representative is smooth, right? But that is just this guy, which is F, let's see here, I guess just X inverse composed with F. Or did I do that wrong? I did that wrong, right? It's what? Yeah, thank you.
So Y becomes the identity map.
Yeah, exactly. Precisely. So n is equal to the real numbers with the identity map. That's the standard definition of smooth function. Right? We assume essentially that it's like the definition of smooth map, except with the real line having its standard smooth structure. So yeah, that's what we mean by smooth function. Okay. And the same would be true if we replaced R with like a C for a complex valued function. Same deal. But then, of course, because we can just use the identity map on the complex numbers thought of as R2 as the chart there, yeah.
Do we always go from a chart to something else?
Well, so what are we doing? Like the whole idea here is to take whatever thing we're thinking about up on the manifold and to bring it back down to Rm and Rn.
Euclidean space.
Because we already know how to do calculus on Rm and Rn, and so we're going to use, it's all thievery.
Yeah.
It's all theft. We're just lifting the calculus from Rn up to the manifold.
So we just take our business elsewhere.
That's right. So like that's a great question because it leads me to the next definition, which is like, what's the derivative? How do you differentiate on a manifold, right? I should probably tell you that at some point because that's the whole point, right? I mean, So here's the definition. This is from page 24 of Jeffrey Lee's book. Let UX be chart on manifold M with P an element of the chart domain. We write X equals to X1, upper 2, upper N as usual. By the way, if you guys use lower indices for examples in the homework, I'm like not going to take points off or anything. Like sometimes for a specific example, it's convenient. It's just, you won't even realize you're doing it, right? You'll be using like lower subscripts where like in our general theory, we put up our subscripts. Like I'm not going to, it's okay. All right, so so here's the deal. For F in, now he has C1M, so here we F, if this is an element of CK, and here we're talking about Rn to R, then F is an element of CKM. That's the notation. So like if it's K times differentiable as a function from Rn to R, then that makes the function K times differentiable on the manifold. Of course, this has to be, you have to be able to do it for each chart. Like you may not be able to do it for, there's not going to be one chart that covers the whole manifold, right? So you have to have every local coordinate representative of the function is K times differentiable to get that it's K times differentiable. So if K equals 1, that just means one derivative. Again, we're almost always assuming smooth, but I'm just saying a little bit about CK here and there to make sure you've heard of the concept. All right, so.
What is the codomain? M is the domain of the function. What is the codomain? Is it
Reals. So that notation means real valued functions. So yeah, that's technically, yeah, good question, Ernesto. So that is really C1 of M comma R if I drop back to the other clumsier notation. But in the case of functions, we don't want to write R. We just want to write, so it's such an important case, it gets its own notation. And by and large, I'm going to erase that 1 and put an infinity because I want to talk about smooth functions anyway. But all right, get to the point here. We define function partial f partial x upper I on u by, and he gives a rather, you may not like this, guys, but he gives you a definition based on a limit here. And, you know, it's sometimes helpful to have this if you're doing, mostly this is helpful if you're doing a super easy problem where the solution in the other notation just looks like notation. So sometimes it's helpful to have this just to kind of see through what's going on. So what's going on here is that I'm only varying the ith component, all right, of the coordinate representative of f. That's what's going on here. Where, and here's the kicker, x of p is equal to a1, a2, a sub n. So the a's aren't really variables here, they're a fixed point. The only thing that's varying in that expression above is h. All right. Now, that is, and here's the definition I saw in my manifold theory course. And you know, listen, guys, it took me a time to really absorb this definition and learn to work with it. And I was struggling with the same thing you guys are now, which is like calculating inverse maps and like, you know, understanding how maps map. Like it's not something you've done a lot before, right? So The struggle is real. Anyway, here it is. Partial f, partial xi of p is equal to partial I of the coordinate representative, f composed with x inverse, evaluated at x of p. Or if you like, you could write it in terms of partial composite of f with x inverse with respect to u upper I at x of p, where u1, u2, dot, 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 un denote standard coordinates on Rn. So that right there, that's the definition of the derivative of a real valued function on a manifold. How do you do it? You take the function, right, up here, and you basically pull it back down here, and you differentiate this thing, and that defines the derivative. So everything runs through the charts. Everything runs through the charts.
I guess we differentiated the function f composed with x negative 1 at some point in x of u, like on the chart.
Mm-hmm.
And that function is taken to the reals.
Like this.
Like that derivative. Like we've differentiated f composed with x negative 1, the diagonal arrow, that function, and we are at a point in x of u down there.
Let's see if I can come up with something silly that we can do. Oh man. I will make a video working through the one you guys were asking me about at the start of class, the what was that? The 1.3, I don't remember. I'll find it.
It was 139.
139. So I'll make a video of that and post it so you guys can like that. I think whatever I do in that video, it will make problem 40 like stupid. I think. I'm pretty sure.
This function is called the partial.
I don't think that problem is actually that hard. It's just a matter of like understanding the notation. But I want to do also, I want to work out a few of the other examples for you guys. So like I'll try to make a video which helps you with the homework is what I'm trying to say, all right? But sadly I can't go over time today, so, and what's going to happen if I start getting into it right now is I'm going to get just far enough into it to not get done with it, and it's going to be really annoying. So, yeah.
Is this a partial or?
This is the derivative on the manifold. But let me do one example of this really quick. So we should have at least one example for today, right? So how about this? We look at the manifold as our 2 by 2. All right, and I'm going to let my function from m to the reals. What's a nice function from a matrix to real number? Any choices? Interesting.
The first number.
Oh, the first number? Well, yeah. But I'm going to do this.
We gotta make them work a little bit harder.
I'm going to do this, all right? I'm going to do determinant of A.
Okay.
And so the coordinate chart I'm going to use, and let me use let me use A11, A21, A12, A22. I mean, there's different orders you could take. This is sometimes called vec. Vec takes the columns in the matrix and just puts them one after the other, after the other, after the other. This makes formulas really nice. If you look at a really sophisticated numerical linear algebra book, you'll see it used. I think Gullum or Gullub. Okay, anyway, so that's a coordinate chart, a global coordinate chart on R2 by 2, right? Okay, so what is, and let's see here, what else do we have? This is, of course, what? This is, see, I probably should have made this a homework. Oh well. Maybe I can soup it up and still make a homework out of this, right? This exact problem. So there's your formula for the determinant, right? All right, so if I look at f composed with, I guess I should have called that x of a to keep it simple here. F composed with x inverse of, and I should use like just sticking with the notation here, this is what it looks like. U1, U2, U3, U4, okay? What is that? You have to work it out logically. So like x inverse of that U1. See, I can't, it takes me a while to get back in the swing of putting these indices up. But this, of course, would be exactly U1, U2, U3, U4, okay? So we're looking, this is the determinant of U1, U3, U2, U4. Of course, you know that that is U1, U4 minus U2, U3. All right, so what is then, now that we've done all this legwork, we can calculate like what's partial f, partial x1. It is, you know, partial U1 of U1, U4 minus U2, U3, right? Which is, well, you guys know how to differentiate, right? U4, it's U4. Now, I'm supposed to do what? I'm supposed to evaluate that. Now, the P here, I would suggest that we use A for P. A is the matrix, right? So the point is the matrix in this context. So I'm supposed to take this thing and evaluate it at, you know, x of A, right? What does that mean? That means I set U 4 equal to A22. So this is literally A22. By the way, if you had just done this, what would you have gotten? Oh, but that's not the relevant one, is it? What is x1?
U1.
Which is A11, right? So what would this given you? Yeah. But this is a way to make that. This is just.
Shorthand?
Yeah. I mean, this is what anybody would guess, I think, if they never had a, you know, darken the doorstep of a manifold theory course. And yet, this is also what this rigorizes.
Are we going to be writing it like that? Like the last way you wrote it? Or are we going to be doing like the hopping around?
I think the hopping around is what you need to do to start with to make sure you understand the definition. But I have made homework problems in the past where the point of the homework problem is to empower you, to encourage you to the fact that yes, at the end of the day, it is just this, right? But we don't want to just write that down without understanding either, right? We want to understand that as part of a coherent narrative. Okay, so what are the properties of the manifold derivative? What do you think? What if I had like two functions? Do you guys think this is true? Like what if I have partial xi of f plus g? What do you think it's going to be equal to?
Partial xi of
Uh-huh.
plus partial xi of g.
Yeah, right. And why is that going to be true?
Because it's linear.
Because it's linear. Because of what? Because it's linear. I like your style, but I would ask you, what is the it?
Because the derivative.
Oh man, son of a gun. Look at that. Oh, phooey. Sorry. You guys get what you pay for online. What can I tell you? You know, start a Patreon for me. Maybe I'll do better camera work.
The derivative is a linear operator.
The derivative is a linear operator. It is, in fact, a linear operator. And we can also prove that if we have a product of two functions, we get ye olde product rule, right? Excuse me. The way these are proved, all right, is to basically, like, let me show you. I won't do all of them, so you guys can do some of them. Yeah? Which one do you want me to do? Let me leave I guess I probably should do the product rule. That one's kind of a little fussy as they go. I don't know. So what is fg defined to be, by the way, guys? Fg of p is, by definition, f of p, g of p, right? So it's the product of f and g, the pointwise product defined. Okay, so when I look at, the real issue is just this. Fg, when you compose it with the inverse of a coordinate map, inverse of a chart, right? How does that work? Well, if you take this thing and you feed it some point, let's call it u, how's that go? So you've got Fg being fed x inverse of u, right?
You go left or right? Or no?
I'm not inversing the whole thing. I'm composing the product function with x inverse. So that means I take the product function and I feed it x inverse of the input. But then, by definition of product, that's f of x inverse of u times g of x inverse of u. Which, if you tilt your head and squint, you can see that that is nothing more than f composed with x inverse, product with g composed with x inverse, all of u. But this holds for all u, right? This holds for all u in Rn. Okay, fair enough. I really should say for all u in x of u. You know what I mean? For all u in the image of the chart domain. Okay? For all u which these things are defined, that's an identity. Therefore, we have what? We have that Fg composed with the inverse chart is in fact equal to the product of in other words, the local coordinate representative of the product is the product of the local coordinate representatives. But that's a product of functions from Rn to R, so we can do calculus 3 on that. See, when I take the partial derivative of this, I take the partial derivative of the product of two functions on Rn, so then I can use the ordinary product rule from calculus 3. And then I just have to basically go back through the definitions to see that that proves this. I'll let you guys do the details in your homework. I think that's actually a pretty good homework problem. It's certainly more entry level than some of the problems I've just assigned you in chapter 1 of Jeffrey Lee's book, right? Some of those are kind of tough. So while we're waiting on getting to the point of understanding those homework problems, let me suggest something that